Hey everybody, today is a little bit about that crazy owl. Ah, there he is, reading the books all the time. Always got his nose in the book. So, this is about angular speeds. So you know how to find tangential velocities. That's a new term, tangential velocity. That's just your speed, your distance per time. That's tangential velocity. But we're going to find something in a different kind of unit when things spin, like these turbines. Um, so kind of some green energy. It's a pretty big deal right now. They need a lot of technicians to keep this stuff working and everything. And you definitely have to know about radians per second, revolutions per minute, and all that stuff, or how you measure angular speeds when talking about such things, and angular displacements as well. So rotational inertia, that's at the end of the year. So we're going to get more into those units later on. But since we're doing centripetal forces and acceleration, we also have to differentiate between what's a speed, which we're going to call tangential velocity from now on, and an angular velocity measured in radians per second, but in this country, revolutions per minute. All right, let's get going, guys. So our objectives, okay, so we're going to talk about angular displacement and angular velocity. We're going to use some angular terms, some theta, some W-looking things, which is lowercase Greek omega, and compare that to the similar type of measurement. This is a displacement, angular displacement. This is a regular displacement, not through an angle in a straight line. And this is angular speed. We're going Greek for this stuff, and this is just your regular speed, your distance per time. Velocity be displacement per time, but since we don't have a displacement for one full turn, we're really talking about speed, not velocity, because your direction's actually always changing when things are spinning. Alrighty. So then we're going to apply those relationships to the world around us. Here we go, guys. Got some bugs. I know how much you guys love your bugs. So this thing's rotating. Oh my goodness, look at that go, guys. Which one's moving the fastest? The inside bug or the outside bug, or are they moving at the same speed? Let's back that up and try that again. And oh, look at that. Which one's moving the fastest? Well, this one goes a greater distance. So in terms of speed, it does have a higher speed because in one turn, it's going to go a further distance. They all have the same displacement after one turn, which is 0 because they're at the same spot. But in terms of distance, the bug on the outside moves a further distance in the same amount of time that the inside bug is moving. So it is moving faster in terms of speed, not angular speed, regular plain old speed, distance per time. This unit, we're talking about an angular displacement. How does this angle for the inside bug compare to this angle for the outside bug? Compared to this angle way out here, it's all the same angle. So we're talking about angular velocity. Actually, they have the same angular velocity. It doesn't matter where the bugs are. They're going to make the same number of turns per second. You're going to take the same amount of time for each bug to go around once. One bug will have a faster speed or tangential velocity. And the reason we're going to call that a tangential velocity is how fast the bug would move if it no longer was on the platform, if it moved in a straight line in a tangent. A tangent being a line to a circle that only touches one point right there. Okay? So it's going to move at a tangent there, but of course, if it sticks to this spinning turntable, there's something pulling it out of a straight line. We'll get to that later on, though. Okay, so these we're going to use for angles, and they both do the same angle, so they have the same angular displacement because they move through the same angle. So both bugs have the same angular displacement. Okay, so it's easier to talk about than the distance because it's the same amount, same angle. So if we consider a disc now rotating from A to B, like so, alrighty. The angular displacement is not the distance any part moves, because different parts move different distances. It's the angle moved through. Okay? So we have a lot of ways we can measure that thing. We can measure in revolutions, we can do it in degrees, or we can do it in radians. One thing you probably already know is that in every single turn, it's 360 degrees. So there's no difference between an angle of one revolution. That actually is an angle. It's one turn. You move through one whole revolution. That's an angular displacement of 1 revolution, which is an angular displacement of 360 degrees, which is an angular displacement of 2 pi radians. So you've done this radian stuff in your math classes, but a lot of you didn't understand why or what that's all about. In physics, it makes some number crunching a lot easier if you do things in radians and not degrees. You'll see why coming up. Okay, so even though you're comfortable probably with degrees, and we know 90 to here, 180 to there, 270 there, and 360 to here, we're going to do things in terms of radians, in half a pi, a full pi, 3/2 pi, and then in 2 pi coming back over here. More on that in just a moment. Okay, so the best way to measure rotation is actually through going to be the radian. Okay, it's going to relate to the radius here, taking the radius off and bend it around. Okay, all right, so what is this radian thing? So radian is the angle cut out and is defined as the curved distance divided by the radius of the thing. So if this thing would happen to spin and S is the same as the R, so you bend through 1 radius, that means you've gone through an angle of 1 radian. So that distance divided by that distance is already in radians, which happens to be 57.3 degrees. Now you might say, how do you get 57.3 degrees? Well, let's talk a little bit more about what 1 radian is. I'm going to have to go to my drawing utensil here. So let's say, and I'm going to use, let's use red. So let's say this S distance right here, oops, I guess I'm not writing. Let me go back to that sucker. You thought it was you thought I was done, and I was not. I got to click the red. Hallelujah. So let's say this S distance right here is the R. You take the R off and you bend it around. How many of those can you fit in a circle, do you think? Well, let's just try it out. So there's 1 radius. Okay, there's a second bent radius. Then I'm going to take a 3rd bent radius. And there it is, guys. That is 2 radians, an angle of 2 radians from there to there. An angle of 3 radians from there clear to here. And you noticed I'm almost to the halfway point. This is a 3, by the way. Seriously, that's a 3. 3 radians. So I'm missing a little bit right here, guys. You see that middle amount I'm missing here? Anybody care to guess how much I'm missing of a radius there? It's a 0.14, because in any circle, in half of a circle, you can fit 3.14 bent radii right there. And 3.14 is pi. Sure, it's more than that, 3.14, I don't know all the numbers. Some people love to memorize that. I'm not one of those people. Okay, so that's where pi comes from. Let's say maybe if you use a smaller, what if you had a smaller radius than that? Okay, I'm going to go green this time. Okay, so now I'm going to use a circle that's this big. Okay, this is my circle. Okay, there's my radius. So I take off 1 radius, it goes to there. Okay, take off a 2nd radius, it goes to there. Take off a 3rd radius, it goes to there. Lo and behold, half a circle is still pi radiuses bent around the outside of that green circle. So it doesn't matter how big your circle is, pi is how many bent radii you can go around there. And the definition for what 1 radian is, it's the angle cut out by moving a distance of 1, whoops, I don't know where that came from, moving through 1 bent radius. That's 1 radian. 2 radians is this angle, 3 to here. Now we can keep on going. There's 3, keep on going. There's a 4 radian, there's a 5 over here, and there's a 6 over here. And Dios mío, what are we short here, guys? A 0.28, because it's 2 of the 0.14s. 0.14 plus 0.14 is 0.28. So this is 6.28 radians for 1 full circle. And 6.28 is 2 pi. So in other words, in 1 full revolution, you have 2 pi radians. So in 1 revolution equals 2 pi radians, which, yes, it's also 360 degrees, but we're not going to use a lot of the degrees, guys. Sure, we used that when we did our vector stuff, when moving in straight lines and everything. But moving through an angle, we're going to find it actually handier to work in radians, because what the reason is, it's easy to go from radians per second to meters per second. Because a radian, the distance that you move through in 1 radian, is the radius. So because of, if you know the length of the radius, it makes it very easy to switch between angular velocity and tangential velocity, which is just the speed. Okay? All right, let's keep on rolling. I know you guys are excited about some practice problems coming up, so let's hit a practice problem. All right, so we have a rope wrapped around a drum. That's 50 centimeters, half a meter. Think half a meter instead of 50 centimeters. It's going to make the math easier in the cranium up here. How many revolutions of the drum are required to raise the bucket a height of 20 meters? So the bucket goes up 20 meters, right? So how much rope do you wrap around here? 20 meters. Well, if you want to know how many radians that is, or revolutions, oh, I guess it asks for revolutions. Well, you're going to have to do a little conversion. I was thinking it might be in radians, because it's an easy answer in radians if this is a half a meter. Because how many halves fit into 20? That would be 40. That means you get 40 bent radiuses bent around here is how far this goes up, which is 20 meters. Okay? So 40 radians is the angular displacement. In radians, they're asking for revolution. So pretty much all this stuff is conversion stuff. Okay? So in this case, first they find the radians. So we're doing what I just did in my head. It's 20 meters, which is the distance bent around the outside. That's the S, the arc distance, not displacement, arc distance around there, divided by the radius. That means that goes in 40 times. It goes through 40 radiuses, or goes through an angle of 40 radians, which is a few turns. So to find out how many turns, now we're going to do a little conversion here. And the conversion is 6.28 or 2 pi radians per revolution. So just convert. So you got 40 radians, so now you divide out by the radians, because you want to get rid of the radians, but you want revolutions left over. So you're dividing out by the radians cancel out. So that becomes 20 divided by pi, which is 6.37 revolutions, which is an angle, which is 40 radians. It's all the same angle. And if you wanted to change that degrees, take this number times 57.3. Because remember, you bend that around, at 1 radius around, it cuts out an angle of 57. Oh, how do you get 57? Well, there's 360 degrees in a circle, right? 360 degrees in a circle divided by 2 pi, that's where the 57.3 comes from. So every radian is the same angle as 57.3 degrees. Okay? All right, let's keep on rolling here. Example 2. Bike. Radius of 25 centimeters. The wheel makes 400 revolutions. How far will the bike have traveled? Well, guys, I would try to get this into radians, because if you know how many radians is, that's just 1/4 of a meter up here, right? So you can use that to figure out how far the thing's going to go. So probably the best route is to change that 400 revolutions into a radians first. Okay, so we divide out by the revolutions, which means times 6.28, and that means it goes through 2,513 radians. That seems like a lot. It's the wrong number, sig figs, but whatever. So now that you're in radians, it actually is pretty easy to change it into a distance, because we know what the radius is. That means you move through 2,513 quarter meters, right? That's all it means. You did a quarter meter 2,513 times. So you're just taking 2,513 radians times 0.25 meters per radian. They don't have that on there, because in physics you normally don't write the per radian, but that's what it is. This is per radian. Radians cancel out, and shazam, 628 meters. Okay, pretty exciting stuff, huh? Alrighty, angular velocity. We're going to pick up right from here with one more little video, because we're going to run out of time, and I want to make sure this is YouTubed. Alright, see you in a moment.